Now it's time to do some practice involving polar coordinates. So we're going to take some time to sort of see, how does this coordinate system work? Jump back and forth between the coordinate system we're familiar with, Cartesian coordinates, and our new system, polar coordinates. And it all comes with practice, learning how to describe things. So do as much as you can. If you're following along with the video, make use of the pause button. See a problem? Try it out yourself and see how you do. And if you need any help, I'm there to help you. Just need to unpause me. Well, let's begin. So, our first problem. Sketch and identify the following curves. All right, well, how bad could that be? So, part A, theta is equal to pi fourths. Now, what is that? If we think about our plane, so I'm going to draw the axes, not because we're in Cartesian coordinates, but just so we have a reference point. So, what does theta equal pi fourths means? Well, it means you go an angle of pi fourths. So you always start theta equals 0, that's the positive x-axis, and then we rotate counterclockwise, so we go an angle of pi fourths. And now you say, well, look, how far out do you go? What's r? Well, there is no r, which means it's arbitrary. So we can go out any amount. So we can start and we keep going out. Now, of course, if we allow ourselves to have negative r, and it depends on who you ask whether or not we allow negative r. But generally speaking, we're like, okay, we'll accept that negative r can exist. Then even though you're facing towards pi fourths, if you go negative r, you would walk backwards. So there we go. That's it. It's the line y equals x. Okay, well, great. Beautiful. Now, we could have seen this in another way. We could have said, hey, remember something? We had this nice fact. Take the tangent of both sides. Tangent of theta is tangent of 1/4 pi. Well, tangent of theta, it translates into y over x. And tangent 1/4 pi is 1. So we end up with y equals x. That's how we could have seen it if we said, look, I don't even want to even try anything in this new coordinate system. I insist I go all the way back to Cartesian. Well, you can do it. All right, part B. So, r equals to cosecant theta. Now, cosecant, that's a curve we don't see very often, right? So, it's not so clear what it looks like. At least we don't know it off the top of our heads, many of us. But it has this, if you just graph cosecant in Cartesian coordinates, it sort of alternates between a u and an upside down u as you move from left to right. So how are we going to do it? Well, we say, look, what is cosecant? Cosecant is the same as 1 over sine. So we can say, look, this is the same as r equals 2 over sine theta. All right? Now, let's get rid of fractions. Fractions can be tough. That's the same as saying r sine theta equals 2. And now we say r sine theta, well, that's nice. You see, that is something that translates nicely between the coordinate systems. And you may say, why? And our response is, exactly. What? What do you mean? No. Why does it translate nicely? Well, because r sine theta corresponds to the variable y. So you get y equals 2. And now we say, oh, well, we can graph that. So if we think about our plane, so we draw our axes, then we have this line here, y equals 2. And now we say, that's so elegant. Very, very elegant. Much more elegant than 2 cosecant theta. And you might be saying, we should abandon this polar. No. Look, y equals 2 is set up for Cartesian coordinates. So of course it's going to look great in Cartesian coordinates. We'll do some examples later on where we have things that look terrible in Cartesian coordinates, and whoosh, it becomes beautiful and polar. But for now, let's keep going with what we're doing. Okay, now part C. And our initial reaction is like, whoa, what? that looks crazy. What could that possibly be? Well, let's think about it. What do we have here? Well, I am a fan of not having fractions. And I see a fraction. So, let's get rid of our fraction. Cross multiply. So in particular, if we multiply the cosine theta plus 2 sine theta across, we get r cosine theta plus 2r sine theta equals 3. And now we're like, I see where we're going, because we have r cosine and r sine. These are really wonderful for translating back and forth. R cosine theta is x, and our sine theta is y. So we get x plus 2y equals 3. Or, if we wanted to, we could solve for y, because we now see what this is. It's a line. And so subtract x, divide by 2, we get y equals minus a half x plus 3 halves. So, what does it look like? Well, we sketch our coordinate system here. We have an intercept at 3 halves. So let's say it's here, 3 halves. And it's not so hard to see. We have a slope of minus a half, so it's going to take us a while. We'll get over here at 3. That's where we'll hit on the x-axis. And now it's a straight line. So again, look, some lines through the origin really clean. Lines not on the origin, kind of a little bit messy. That's all right. These are all lines. Wow, interesting. Probably wouldn't have guessed when we started, but we don't want to guess. We want to figure it out. So, good. Well, let's try another problem. Okay. Identify and sketch the curve r equals 6 cosine theta plus 8 sine theta. Okay. What could this be? Well, what we want to do is, we're not quite comfortable with polar yet. We've had a lot more practice in Cartesian. So let's think about how can we translate this into Cartesian. And we think of our basic things that translate nicely. R squared, r cosine theta, r sine theta. Those are things which have a nice translation from our polar coordinates into Cartesian coordinates. And we say, well, wow. We have r, not r squared. We have cosine theta, not r cosine theta. And we have sine theta, not r sine theta. So close, so close. But then we're like, but wait a second. We can do something. So we can take this expression and say, if we had r's, life would be good. So let's put them in. So we're going to multiply by r. So we're going to multiply by r. And let's see what we have. We'll get r squared equals 6r cosine theta plus 8r sine theta. And now we're like, hey, this is great. R squared. That becomes x squared plus y squared. R cosine theta, x. R sine theta, y. And now we're like, okay, I think I see what's happening. When we see an x squared and y squared together, we oftentimes think circle. So we're probably thinking this could be a circle. Well, we got to put the 6x's and 8y's over here. So let's see, x squared minus 6x plus y squared minus 8y equals 0. So I've just moved the 6x and 8y across. Now, what do we want? Well, we'd really like the first term here to be a nice perfect square. Something squared. So right now, it's not that. It feels somewhat incomplete. So is there a way to complete the square? Well, yeah, there is. Completing the square, right? Take the middle term, divide by 2, negative 3, square that, and you add it to the end. So plus 9. Good, good. Okay, similar thing over here. Wait, let's finish. We didn't finish our thought there. That becomes x minus 3 squared. What else do we have to do, though? If we add 9 here, we have to compensate. And the way we can compensate, well, we can do it by either putting a 9 there or subtracting a 9 there. Let's put a 9 on this side, plus 9. All right, y squared minus 8y. Well, complete the square again. All right, what do we need to do? Middle term divided by 2, square, plus 16, plus 16. And this will become y minus 4 squared. So x minus 3 squared plus y minus 4 squared equals 25. So we say, well, now we know what it is. It's a circle. And we can talk about the center. The center here is at 3, 4, and the radius is 5. So, okay, r equals 6 cosine theta plus 8 sine theta is a circle. Now, we should sketch it, and we should do it because it tells us to do it. And of course, if it tells us to do something, we're going to do it because after all, we want to make sure we get all the credit, right? So, what do? Well, we go over 3 points in x, 4 up in y, so roughly here. That's our center. And the radius is 5. Well, you can check the distance from the point 3, 4 to the origin is actually 5, so it's going to pass through the origin. And so we get the following circle. Well, something like that. So there we go. 3, 4, and radius 5. And that's our picture. All right. Great. Beautiful. Beautiful. Okay. So let's keep going. Doing well so far. Now, sketch and indicate the region where r goes between 1 and 2, and theta goes from 0 to pi over 2. So this is actually very simple to describe, right? We're just saying, well, r goes between 2 values, theta goes between 2 values. What does it look like? Now, in Cartesian coordinates, when we talk about, well, x goes between 2 numbers, y goes between 2 numbers, we're like, ooh, it's a rectangle. Well, what would it be in polar? Well, let's think about it. When we talk about r equals 1, what would that be? Well, we always talk about in relationship to the center. So r equals 1 would be all of the points which are distance 1 from the center. So if I talk about all points a fixed distance from a location, what we get is a circle. And so it's a circle of radius 1. So that's r equals 1. Now r equals 2, same idea. It's going to be all the points that are distance 2 from the center, so it's just a bigger circle. So radius 2, twice the radius. Okay, so now we have 2. If we say, look, r can go from 1 to 2, well, what does that tell us? Well, that means we can be any distance from starting from 1 going out to 2. So what it corresponds to is this sort of flat donut. If we wanted to be very fancy, we would call it an annulus, but that sounds hard to spell, so we'll call it a flat donut. Okay, so there we go. That's just if all we use is information about r. Now, there's other information that we need to use, and that's about theta. Okay, so what is that? Well, theta says that we should be between 0 and pi over 2. So theta equals 0. that's what we usually associate with the positive x-axis, and theta equals pi over 2, we associate with the positive y-axis. So, generally speaking, when we talk about being between theta is 0 and pi over 2, we're going to mean what happens as we sweep out. So, now I'm going to be slightly ambiguous from what I said before and say, generally speaking, we're going to just assume that we're up here in the first quadrant. And this gets to the, the ambiguity. What do we do about negative r? So we could talk about things down here, but we'll get into a second here. What do we want to do? Well, now our goal is we want both things to be true. So we're going to cross our eyes and see where they overlap. And where do they overlap? And the answer is they do in the following way. So it's going to be 1 to 2, and then we just need to shade this in. Now, here we can start to justify saying, well, even if we had decided to include this, which there's some ambiguity about whether we would, and I wish I could say definitively this is what we should do, it would have to be negative values for r if we were down here. But r is strictly between 1 and 2, so we can't go in that direction. So this truly is the answer, whether or not you accept the ambiguity. So, all right, so there we go. That's great. So it turns out that we don't get rectangles here if we just say, oh, r is between two numbers, theta is between two numbers. What we get are essentially sort of, you might call them like pizza crust or pie crust, where you have, this is a very thick crust, by the way, and parts of these pieces of wedges of circles. And so that's our sort of our basic fundamental shape when we think about polar coordinates. Now, our problem is only halfway done. We've sketched it. And this is the first part. The second part says, well, hey, let's describe this in Cartesian coordinates just for comparison. Well, here's where things get messy. Remember, we said we have two coordinate systems, and depending upon what coordinate system you have, some things are better than others. Let me give an example where lines were great in Cartesian, kind of looked messy when we went to polar. But here, we say, look, this is set up for polar. This is where polar has the advantage. And now, I suspect, Cartesian, maybe not so great. Well, let's try it out. What'll happen? Well, let's resketch this and just label things using our Cartesian coordinate system. We have, well, there's four bounding curves, and so we should take all of them into account. So what are the four bounding curves? Well, this bottom part here, this left part, this sort of inner circle, and this is outer circle. So, what do we need? Well, we have to be somehow saying, look, I've got to be above there. So, we need to have x has to be greater than or equal to 0. Okay, that'll make sure we're above there, and that'll capture that boundary. Whoops, not x, that's y. I got ahead of myself. X greater than or equal to 0 is going to be from here. Okay, so that says we're definitely going to be from here, we're definitely going to be there. Now what else do we have? Well, we have to be sort of out, away, and this inner circle has to be a bounding curve. So the square root of x squared plus y squared has to be greater than or equal to 1. Okay, and we have to be inside this other circle. Square root of x squared plus y squared has to be less than or equal to 2. And that's it. Now, ultimately, it might be the case. So, for instance, suppose we wanted to set up something about a mass problem, which we could do. We certainly could do it. And we want to say, well, we want to find something about mass here. We'd have to set up an integral. This is certainly a nice way to describe it, but if we were setting up our integrals, let's say we're integrating with respect to x, we'd have some challenges because we'd say, well, look, you'd have to split it at this point. So you might say, well, for 0 less than or equal to x less than or equal to 1, you'd have the bottom curve, which is the square root of this curve right here, would be, well, it's x squared plus y squared equals 1, so it's the square root of 1 minus x squared. That's less than or equal to y, less than or equal to the square root of 4 minus x squared. That's the piece here. And for 1 less than or equal to x less than or equal to 2, now the bottom curve is 0, and the top curve is the square root of 4 minus x squared. And that's the piece there. And you see, wow, that's getting messy. Yeah, it can get messy. And so it's sort of, the idea is choose the right coordinate system that helps you describe the shape in the simplest way. We're not making new coordinate systems for the sake of making new coordinate systems. We want to make a new coordinate system because we want it to help us. And the way something helps us is if it simplifies. That's our goal. Math is just about one simplification after another. And if we simplify things enough, then maybe we'll be able to answer that question. All right, well, let's try some more problems. So here, we're going to convert things into polar coordinates. And we'll see what we get. Okay, so what can we do? Well, we'll just work our way through them. Now, our basic collection of facts is the following. X squared plus y squared equals r squared. X equals r cosine theta. Y equals r sine theta. And these should be our primary ones. In a pinch, if we're having a struggle, there's one more, which is that y over x is equal to tangent theta. But if you look, it actually just falls from the two above. You see y over x, well, the r's cancel, sine over cosine is tangent. So what we're going to look for is we're going to say, well, let's look for things that look like x squared plus y squared. And if we don't have those, well, we can just substitute in for x, we can substitute for y, and then we do a lot of cleaning up. Okay, well, let's begin, right? Part A. What could that be? Well, we probably can start by expanding. We don't have to jump in right away, because if we expand, we're going to get an x squared. We already see a y squared, and we like x squared plus y squared. If we can get that, our life is good. So we have x squared minus 6x plus 9 plus y squared equals 9. And now we're like, hey, this is great. The 9's cancel. And x squared plus y squared is r squared. And then here, minus 6r cosine theta equals 0. Well, move the term across. R squared equals 6r cosine theta. And now r equals 6 cosine theta. There is a small epsilon cheat we just did. I want to explain what that epsilon cheat is, just in case anybody ever challenges you in the future. You can say, oh yeah, I know about that small epsilon cheat, but here's why we're okay. So our small epsilon cheat is we divide by r. You're probably thinking, oh, that sounds fine. You divide by r all you want. Well, here's the thing. You should never divide to cancel unless you are 100% sure you're never going to divide by 0. So how do we know r is not 0? Well, it could be 0, and that's a possibility. But the thing is, at the end, we say, well, look, we see there are times when cosine of theta is equal to 0, so we're still going to get an r equals 0 out of this equation. So we're fine. We didn't lose anything by dividing it out by r. And it's essentially always going to be the case that that's true. So go ahead, divide by r, you'll be fine. Okay, now of course somebody out there is like, and they're going to try to come up with something crazy. It will be completely artificial and it'll be nonsense. Forget it. Come on. All right. Now, x cubed plus y cubed equals 9xy. You're like, well, x squared plus y squared is great, right? It is wonderful, isn't it? We don't have that. So what do? Well, if we can't do anything else, we say, put in what is x, put it in what is y, and simplify. So I don't see anything else. So here we go. We're going to have r cosine theta cubed plus r sine theta cubed equals 9 r cosine theta r sine theta. Okay, well, if we cube this, we're going to get an r cubed and an r cubed there. So go ahead and factor out an r cubed. Then we get cosine cubed plus sine cubed. Okay, equals over here 9r squared cosine sine. Hey, there's lots of r's. Let's go ahead and cancel them out. So we can r squared r. And now we say, perfect. We can solve for r. And indeed, the desirable thing for us is to write r as a function of theta. Similar like in Cartesian coordinates, we're like, ooh, y is a function of x. We really like that. For us, we want r as a function of theta. So, in our case, we say r equals 9 cosine theta sine theta divided by cosine cubed theta plus sine cubed theta. And there we go. That's about as simple as we can hope for now. Okay, good. Still have one more. All right, let's do the last one, part C. All right, what do we see? Well, that looks terrible. That's a terrible looking expression in Cartesian coordinates. I don't know if we could figure that out. But let's proceed. Well, we see an x squared plus y squared. Okay, that becomes r squared equals, and then, what else? R squared plus r cosine theta squared. All right, see, what do we do? When we saw the x squared plus y squared, replace it with r squared. There was one x, r cosine theta. And now, great, we've made a lot of progress. Well, let's see, what else can we do? Well, we can take a square root of both sides. So that would leave us to r is equal to r squared plus r cosine theta. Now, you might be saying, okay, Steve, I'm highly suspicious of you taking a square root of both sides. We're okay. It's a different story, but we're okay. Just bear with me, and let's just assume that we can do it for now. And what can you do? Well, everything has an r. Divide out. Great. Beautiful. So we have 1 equals r plus cosine theta, or r is 1 minus cosine theta. And that is actually a nice, really clean expression. We have r as a very simple expression of theta. So we can actually start to understand that. We'd have a hard time, not impossible, but a hard time getting y as a function of x. And if we did, forget it. Crazy. Who knows if we'd be able to understand it. But now we were able to say, all right, we're able to get a rough idea of what this looks like. Now, you might say, well, we don't really know what it looks like, do we? We will next time. We're going to talk about plotting things in Cartesian coordinates. All right, well, let's try another similar problem. Okay, here we go. Rewrite x squared plus xy plus y squared equals 1 as an equation in polar coordinates. Now, you might think x squared and y squared, oh, that sounds a lot like a circle. Well, it turns out it's not far off. The xy, though, does some interesting things to it. And so it's not quite a circle. But, okay, we won't go into it right now. So, well, what happens? Well, what we need to do is just do what we've been doing, right? So we see an x squared and y squared. So we say, okay, really this is x squared plus y squared plus xy equals 1. So x squared plus y squared is r squared. All right, x, r cosine theta, y, r sine theta. Great. And the 1. All right, now this is, what does that do? It's still 1. Okay, all right, it is the 1. Well, this becomes r squared, just pull it out, 1 plus sine theta cosine theta. And that equals 1. Now, if we wanted to be really fancy, and it's kind of fun to do that, what do we see? Well, sine theta cosine theta, it's very close to half angle. Double angle. So if you make a little note here on the side, I'll put it down in the corner. Sine theta cosine theta. Well, if you were to put a 2 here, that's sine of 2 theta. So that tells us that sine theta cosine theta is actually a half sine of 2 theta. So we can replace this. And r squared times 1 plus 1/2 sine of 2 theta equals 1. And now we're like, great, wonderful. Let's move it across. R squared equals 1 over 1 plus 1/2 sine of 2 theta. Now that's r squared. We'd really like to write r as a function, and so we'll say r equals 1 over the square root 1 plus 1/2 sine 2 theta. And we should note, look, a half sine 2 theta can only go from negative 1/2 to positive 1/2. When you add 1, it says it's always at least a half, never smaller. So there's no problem with negative values. So that says, great, beautiful. So we can actually say, look, it works for all values for theta. Now, what does it look like? I don't know. We'd have to plot it. But it should look, well, we can say something. This is a conic section, right? Because all the terms here are quadratic. Conic is just a very fancy way of saying everything involved is at most a quadratic in your polynomial. So it should be a familiar shape. And in this case, it turns out it's a tilted ellipse. So it's an ellipse, but that's been turned about 45 degrees. It's not so clear, But even here, not so clear. But that's what it looks like. All right. Well, let's do a little bit more. Okay. Here we go. Oh, yeah, this curve. Famous curve. It's called the Archimedean spiral. It's named after Archimedes. He's a very famous mathematician who lived in ancient Greek. Or is it ancient Greece? Well, anyways, he lived a long time ago. And there's lots of stories about him. Many people consider him to be one of the great mathematicians of all time. And justifiably, you can say he actually had a lot of good ideas, including calculus. He was doing calculus thousands of years before Newton. Why? Well, because he understood the ideas. Break things up into parts, figure out what's happening, put it all back together, and it works. Now, what's the Archimedean spiral? Well, it's a problem of ancient Greece that, well, they love geometry. And there's a famous challenge. It says, hey, suppose I have an angle. Can we take whatever our current angle is, and so here's an angle, theta, and what they want to do is they said, let's take the angle and split it into thirds. And in other words, cut it so exactly into parts where each one of those angles was equal to each other. Now, there are some special cases where they could do it, but they were having a hard time doing it in general using their technology. And their technology was they could make a straight line and they could make a circle. They call it compass. So that was it. Can you use just a straight edge and a compass? Can you trisect, split into three? And they worked on it, and they couldn't do it. It turns out, for a very good reason, and the very good reason is that it's impossible. Mathematicians figured this out. It took a long time to do it, but they were able to actually show that this problem is impossible. It can't be done. Now, there are still people that exist today who insist it can be done, and, well, everyone needs a hobby, right? They tend to be mostly harmless. But yeah, it's an impossible with only standard straight flat edge and a compass. But Archimedes said, there's another problem, and here's another problem that says, instead of trying to split an angle into three parts, can you split a line segment into three parts? And the answer was, well, yeah, that's super duper easy, and it can be done. Very easy. I'm not going to walk through how it happens. So he said, wouldn't it be great if there was a way to connect an angle with a length? Because then if I wanted to trisect an angle, I would only have to trisect a length, which means I could do it. And so that's the curve. So it's the curve that does something like this. It comes out, and as your angle increases, your distance out increases. So that's the Archimedes spiral. All right, so that's what it is. So as you let theta grow, r grows with it. Now, you might say, okay, kind of a fun picture. How does this translate into our Cartesian coordinates? Well, let's think about what we have. R equals theta. And what can we do? Well, one thing we can do is we could take the tangent of both sides. So tangent of r is equal to tangent of theta. Now, why do that? Well, because we know what to do with tangent of theta. See, tangent of theta is y over x. And we know what to do with r. So that's tangent of the square root of x squared plus y squared. And there we go. Or if you multiply the x across, you could say, look, y is equal to x tangent of the square root of x squared plus y squared. And look at that beautiful formula. Well, it's not that beautiful. It's kind of messy. We can't solve for y as a function of x. See, there is that trapped y there. Can't solve for x as a function of y. And of course we couldn't, because we can see the vertical line test, you'd fail miserably. Horizontal line test, you'd fail miserably. So you can write it as a sort of implicit function here, and it'd be hard to deal with. But you look and you compare, you say, wow, in polar, so clean. Look how clean it is. It's beautiful. It's a beautiful thing to work with, which is why it's nice to have that system of polar coordinates. Now, I will say, I can't say definitively that Archimedes actually expressed things in this format because, well, the polar coordinates really exist. But the notion, this idea of saying transform one problem to another problem, that's a very common notion. And the idea of saying, hey, I'm trying to solve this problem over in this setting, if I can turn the problem into a different setting, I have tools to solve it. So can I get over to there to use the tools? And being able to do that is really powerful and very useful technique. All right. Well, let's see. I think there's one more problem. So let's do one more. Sketch the region described by secant of theta less than or equal to r less than or equal to 2 for theta going from negative pi halves to positive pi halves. So when we say theta going from negative pi halves to positive pi halves, what we're really saying is we want to be in the right plane. In other words, we're going to be on this side. Okay. Well, let's think about what we have. We really have a string of inequalities. So whenever you have a string of inequalities, you should say, let's break it into really two inequalities. So let's start with the first one. Secant of theta less than or equal to r. Well, secant is 1 over cosine. So 1 over cosine theta is less than or equal to r. And we don't like fractions, so we'll multiply. Now you might say, well, wait. I have to be careful when I multiply and there's an inequality because I have to pay attention to the sign. If cosine theta were negative, I'd be in trouble. But now I say, no. Cosine theta is definitely not negative. How do I know that? Because I have a restriction on theta. From negative pi halves to positive pi halves, we're over here in the right half of the plane. X is positive, and that really is telling us that the cosine is positive. So if I multiply by cosine, I'm okay, since I know I'm in the right half. So this becomes 1 less than or equal to r cosine theta. And now I say, but wait, r cosine theta is just another name for x. Okay, so we can really figure out what that means. X has to be greater than or equal to 1. Perfect. Now the other inequality, r less than or equal to 2, we don't have to do anything. We know what that means. See, r is our distance from the center. So we're saying that our distance is at most 2. So if we translate that into a picture, that says we have a circle of radius 2, and we want to be on the inside. So 2 are near. X greater than or equal to 1 says, well, hey, I want to be over here. And now we do our whoop, cross our eyes, and we're going to see a shape emerge. So we're going to help our picture here. We're going to do some dotted lines here just to highlight what's going on. Here's 1, and then we have our circle. You have to imagine that we could draw a circle. Okay, there's radius 2. So minus 2, positive 2, and 2. And we say, okay, the overlap would look like what? Well, it's just a piece of our circle. And we'll shade to fill it in. And therefore, there's a sketch of our region. And it's actually not too bad, right? That's a pretty simple way to describe that region. And we're able to figure it out. So being able to describe things in polar coordinates might be a very useful thing if we want to start doing calculus in polar coordinates. And this is a calculus class, so we'll probably head towards that direction. Well, I think that's it for now. Thanks for joining me, and see you again in another session.